We're going to start this video with a definition. It says a point in the domain of f. I actually want to emphasize this part right here because it's very easy to overlook that. A point that's in the domain of f. So this point must be in the domain of our function, at which either f prime of c is equal to 0, so the derivative is equal to 0 at that point, or f prime of c does not exist, so in other words, the derivative is undefined at that point, is called a critical point of f. Sometimes these are called critical numbers, but they're critical points, places in particular where the first derivative is equal to 0 or the first derivative does not exist. Critical points are possible local extreme values. They are not guaranteed local extreme values. So that's why we care so much about critical points, is because they will end up being possible local extreme values. So we're just going to practice finding these critical points to start off here. The first thing you may want to do is you may want to look at your domain of this function, because remember that these points have to be in the domain of your function. So if I look at g of x here, g of x is 12x to the fifth minus 20x to the third. The domain of this function is negative infinity to positive infinity, because it's a polynomial, right? This is a polynomial. It's a relatively nice, simple function. It's really not going to give us any problems as far as our x values. So what this domain means here is it means if I come up with any point where either the derivative is equal to 0 or where the derivative does not exist, that is automatically going to be a critical point, because my domain is all real numbers. My domain includes every real x value. So I need to consider these two cases. First, I need to find the derivative, so let's find g prime of x. G prime of x is equal to, here I have 60x to the fourth minus, looks like 60x squared. So I have my derivative, and I need to be concerned with places where my derivative is equal to 0 and places where my derivative does not exist or is undefined. Let's take the places where the derivative is equal to 0. This is usually the more common place that will have critical points. So I'll take 60x to the fourth minus 60x squared, set this equal to 0, and we're going to solve for x. So I'm going to factor if I can. I think factoring is always the easiest method to solve these. If you do not factor here, you will lose a critical point if you try and just solve for x without using factoring. So I think that I would factor out, in this case, 60x squared, and that would leave me with x squared minus 1 is equal to 0. Once I have this, I can take each factor and set it equal to 0, or you could continue factoring x squared minus 1. That's a difference of 2 squares there. I would take each factor, I think, and set it equal to 0, so 60x squared is equal to 0, and x squared minus 1 equals 0. On the left-hand side, if I divide by 60, I'll have x squared is equal to 0, and I take the square root of each side, I end up with x equals 0. If you do not factor that first step, if you don't factor at this point right here, you will not find this critical point of x equals 0. It just won't show up in your solutions to this equation. So it's really important that we do factor out at least x squared. Even if we don't get the 60, that's okay. We need this factor of x squared though. So x equals 0, this is my first critical number or critical point here. X squared minus 1, this part you can solve by factoring or by using square roots. That part is up to you. I always prefer to factor, so this is x plus 1 times x minus 1 is equal to 0, which will give me x equals negative 1 and x equals positive 1. So these are two more critical points that I have. Right now I have x equals 0, -1, and +1. So I also need to be thinking about places where my derivative does not exist. But here in this case, look at your derivative. G prime of x is 60x to the 4th minus 60x squared. Again, g prime of x, and I'm actually going to write this out, g prime is a polynomial. And what do we know about polynomials? We said earlier that their domain is -infinity to +infinity. So that means that g prime exists everywhere, which means we're not going to have any additional critical points where g prime of x does not exist, because it exists everywhere. There's no place, no x value where g prime of x does not exist. So that means if you want to, sometimes I'll do this. I put no solution, which technically this isn't an equation. We're not solving anything, but really this just helps me remember that, hey, we're not going to have any additional critical numbers here. So we've got 3, though. We've got x equals 0, x equals -1, and x equals +1. And again, why we care about this is that they are possible local extreme values. They might be local extreme values, or they might not be. But at the very least, it gives us a place to start. Let's look at one more example here. Next, I want to find the critical points of f of x equals 1 over x plus natural log of x. I'm going to start off exactly the same way that I did before. So I'm going to look at the domain of this function first, because remember, if we're looking for critical points, those have to be in the domain. So I'm going to look at each of these separately and then kind of mash together the domains here. If I look at 1 over x, I see that that's going to be a problem for me. Here in this case, x cannot equal 0, because if x is 0, I'm dividing by 0. Can't have that. So that's our first problem with our domain, is x cannot equal 0. The other part, natural log of x, this is perhaps an even bigger problem, because if I look at the domain of this particular part, the domain of natural log of x is 0 to +infinity. We can only take natural log of positive numbers. So here in this case, so it's actually not going to be that big of a problem, because this is the domain just for natural log of x. We said the other problem that we were going to have with our domain is that x cannot equal 0. And if we look at this, well, 0 is not included in this set already, which means that rule is sort of already built in. We don't need to worry about that rule. So the domain of our function is 0 to +infinity. We're going to keep that in mind towards the end of our problem. So we're going to find critical points, which means we need the derivative. So I'm going to rewrite this, I think, first of all. F of x, this is really x to the -1 power plus natural log of x. I'm going to write it that way just so that I don't have to use the quotient rule. So f prime of x, my derivative, this will be -x raised to the -2 power plus the derivative of natural log of x, that's 1 over x. And I'm going to rewrite it. You could leave this with a negative exponent if you wanted, but we're going to be doing a lot of algebra here with the first derivative, and I just don't think we have as much experience working with negative exponents. It's easier to make a mistake there. So I strongly encourage you to rewrite that as -1 over x squared plus 1 over x. And from here, it's kind of up to you if you want to leave this as 2 separate fractions or find a common denominator. I actually think it'll be easier for us in the long run if we do find a common denominator, so I'm going to go ahead and do that here. So I've got x squared, I've got x. I'm just going to multiply this fraction over here by x over x. So this is -1 over x squared plus x over x squared this ends up being negative 1 plus x divided by x squared. So that's what it looks like once we have our common denominator. I think that this is actually going to be easier to work with algebraically. And the reason I think that, let me give myself a little bit more room here. The reason I think that is because now we have our derivative. Remember the two cases we want to think about, places where f prime of x is equal to 0, and places where f prime of x does not exist. So I'm going to, first of all, take this function, take my derivative that I just found, set it equal to 0. So negative 1 plus x over x squared is equal to 0. Now, my first step, I'm going to get rid of that x squared in the denominator, so I'll multiply by x squared. So here, I will have negative 1 plus x equals 0. If you'll notice, this is a rational function. It's essentially just a fraction. This fraction is only 0 if the numerator is equal to 0. So one shortcut you can take, this only works if you have one single fraction, which is why I think this was so helpful to find a common denominator. One shortcut you can take is you can just take the numerator, negative 1 plus x, and set that equal to 0. You'll get the same exact solutions. Just one fewer step to take. But in this case, I'll add 1 to each side. I end up with x equals 1. Here in this case, our domain was not negative infinity to positive infinity. So we want to just check that 1 lies between 0 and positive infinity. Is it in that interval? Well, yes, 1 is between 0 and positive infinity, which means that x equals 1. This is a critical number. Next, I need to think about where is f prime of x does not exist. So again, I'm looking at my derivative over here, and my eyes are drawn to the denominator here. That derivative would not exist if that denominator was equal to 0. That would give us something which is undefined. So I'm going to take my denominator, x squared, set it equal to 0. We can solve this equation relatively easily just by taking the square root of each side. And I end up with x equals 0. So this is a possible critical number. Again, I need to check that this critical number is in my domain, only this time I've got a problem. 0 is not in the open interval 0 to positive infinity. That parenthesis right there on the left-hand side really means 0 is not included in the set. So 0 is not in my domain, which means that 0 is not a critical number. So this guy right here, this is not a critical point because it is not in the domain of f of x. So because it's not in the domain of our original function, it cannot be a critical point. So this is just finding critical points. We're going to be doing this a lot going forward, both in this section and in 4.3. We're going to see this a ton going forward. So get used to seeing these types of problems. We're going to be finding critical points and critical numbers a great deal going forward.